Hello everyone. So in this video I'm going to talk a little bit about about three different topics. These different topics are related to the design of CMOS inverters and CMOS digital logic. Okay, so I'm going to mention in each topic I'm going to mention why exactly these are very important topics that needs to be taken into consideration while designing CMOS logic. Okay. First of all, so the three topics are the noise margin, the second one is the propagation, and the third one is the power, okay, the power dissipation. Let's first talk about the noise margin. What is the noise margin? First of all, let's consider a graph which is the basic graph, the ideal basic graph of an inverter. If you have an inverter and it has an input and an output, so these are two inverters back to back. But let's talk about this inverter first. You expect to see that when you input, that's the voltage of the input, that's the voltage of the output. You expect to see when you have an input voltage of corresponding to logic 0, it outputs A1, VDD, and when you give it VDD, it outputs 0 volts. Okay? And ideally I want it to be this, to have this property, which is an abrupt change. Unfortunately, there is nothing ideal as this scenario is, and that's why we approximate it by this piecewise linear graph. Any inverter is approximated by this piecewise linear graph. Okay, this is not specific to the CMOS. It is for any inverter. Okay, that's an approximation for the behavior of any inverter. We're going to discuss this graph. Okay, and then move on to the CMOS. Discuss the graph related to the CMOS. How is this changed to when we talk about specifically CMOS inverters? Okay, so in this graph you have this kind of piecewise linear behavior. When you input an input voltage that is less than V input low, okay, at most it is V input low, you expect to see an output voltage close to the VDD, which is called the V output high. Okay, and when you input a value that is very high between the V input high and the VDD, you expect to see an output voltage which corresponds to V output low, which is interpreted as logic 0 at the output. Okay, so the V input low is defined as the maximum input voltage that is interpreted as a logic 0 at the input, and thus gives a logic 1 at the output. Okay, if you input a voltage greater than V input low, then this voltage is not going to be interpreted as a logic 1. Okay, it is not going to be interpreted as logic 0 and will not give us a logic 1. So that is the maximum voltage of the of V input low. Okay, V input high is defined as the minimum voltage that is interpreted as a logic 1 at the input, and thus gives us a logic 0. If you feed the inverter with a logic value, with a voltage value less than V input high, which is a value less than this threshold, then you expect that the gate is not going to interpret it as a logic 1, but otherwise it's going to might interpret it as logic 0 or logic 1. It's ambiguous, and that's why it is a threshold value. You should not give if you want to give a logic 1, you should not give the logic 1, you should not give a value less than the input high. Okay? And this defines the noise margin. Okay? Ideally, you're going to be giving V output, you're going to be giving VDD, which is supposed to be close to V output high. Let's assume, for instance, that VDD equals V output high, so pretty much these values coincide. Okay? So the noise margin is defined as, ideally you're going to be inputting a VDD, okay, but if the noise margin, if the noise that comes perhaps from electromagnetic waves surrounding the NOT gate, or perhaps comes from thermal noise or some other sources of noise, then you might expect that this inputted voltage, which is supposed to be VDD, is not going to be exactly VDD. It is going to be VDD minus some value. And you're hoping that this value, which is I'm going to call epsilon, is going to be very small. Okay? So if it exceeds this noise margin, if it's higher than this noise margin, then in that case the V input will be lower than V input high. And that is why I do not want this value to exceed the noise margin. Or in other words, I want to design a transistor, I want to design a logic NOT gate that has a very high noise margin. That has a very high noise margin. And that's why the VDD, the ideal curve is has a noise margin of VDD over 2. Okay? And pretty much that's the same for so this is called the noise margin high. Okay? And this is called noise margin low. Noise margin low. Alright? Noise margin low. Okay? So noise margin low, again, it is the value between V input low and V output low. That's the difference between these two values. Alright? Ideally, I want the noise margin low and the noise margin high to be as large as possible. So the best case scenario is to hope that they are going to be equal to VDD when this curve is very steep. Okay? So, again, the noise margin low and the noise margin high are defined as, a lot of people get confused. Okay? So I'm going to teach you right now a very easy way to memorize these quantities. Noise margin low is equal to the difference between two voltages. One of them is V something low, and the other one is V something else that is low. So V minus V, and this has a subscript of low, and this has a subscript of low as well. The same goes for the noise margin high. Has a subscript high and has a subscript high. Okay? And you take the bigger value, which is the input, which is in that case it's the output. Okay? So it's the input, right? And then minus the output. Okay? V input low minus V output low. Right? V input low minus V output low. So that is the noise margin low. Noise margin low is defined as V input low minus V output low. Again, noise margin high. It is V something high minus V something else high. Which one is higher? The output minus the input. Okay? The output minus the input. Okay? If you do not have this graph, then you need to think about these values. You need to think about these values and interpret them in a very in an easy way so that you can memorize these quantities. The worst case scenario, if you got confused in an exam, take the difference between V input low and V input high. So if you got confused and you do not know which one is output and which one is input, if you want to calculate the noise margin for the low, then you take the difference between input minus the output for the low and take the absolute value. Alright? But here it turns out to be input minus output. So even if you confuse yourself and made output minus input, just take the absolute value and this should give you the noise margin, because the noise margin is always a positive quantity. Alright? And the same goes for the noise margin high. Alright? So let's have an example about a CMOS inverter. Okay? So this pretty much works for any inverter. Okay? So the example says that the VDD is 5 volts, V threshold equals V threshold N, V threshold P are equal to 1 volt. Okay? And the CMOS inverter is a matched inverter, which means that this gate and this gate, these two transistors are matched to each other. Right? What is a property of the matching? That is the Y, that is the input. Okay? This is the output. Alright? What is the property of a matched inverter? First of all, V output high is equal to VDD. Okay? V output low is equal to 0. Okay? These are the properties, two of the properties of the matched CMOS inverter. Okay? Also, actually, these are the properties when it is CMOS inverter. It's not when it's matched. Okay? When it's matched, we have V input low equals and V input high equals. okay? V input low is equal to 1 over 8, 5, 3 VTT, 3 VDD, minus plus twice VT, okay? 1 over 8, 5 VDD, minus 2 VT, okay? What is VT? VT is the threshold voltage. And we're assuming, and if they're matched, then this indicates that this is equal to that. And when they're matched, these two values, these two equations hold. Okay? So when they're matched, these two have to hold, and these two have to hold. Because even when these two hold, but it is not a matched transistor, it is not a matched inverter, then these equations do not hold. Okay? So whenever they're matched, then these equations do hold. Alright? So, the question is, we want to calculate the noise. Yes, and something else also for the matched, which is Vm equals Vdd over 2. Alright? What is Vm? Vm here is the middle point. Okay? The middle point is defined as the point that intersects this line with a curve, with a straight line that is 45 degrees. So that the point that has Vm on the y-axis and Vm on the x-axis. It does not have to be, in general, it does not have to be in the middle between VDD and the 0. It does not have to be that. Perhaps this curve is shifted a little bit or shifted that way. So in that case, Vm will not be equal to VDD over 2. But in the matched case, when these equations do hold, then the Vm is going to be equal to VDD over 2. Okay? What is required? What is required is to calculate the noise margin low and noise margin high and the gain. Okay? And I'm going to define what the gain is in a moment. Again, so this is basically the graph of a CMOS inverter. Okay? It looks pretty similar to this graph, but the difference is this is VDD and this is 0. Okay? And in addition to that, so this V output low is 0. Alright? And in addition to that, this is VDD, okay, which is V output high, coincides on this point, and this is Vm, which is equal to VDD over 2. Alright? So, let's calculate the noise margin. So this is the solution. Okay, noise margin. Okay, let's first calculate V input low and V input high. Okay, so after the calculation, we calculated first V input low and V input high through direct substitution by the values of VDD and V threshold. Gave me 17 over 8 volt and 23 over 8 volts. Of course, they're not equal, right? And Vm is calculated as 2.5 volts. The noise margin low is defined as V input low minus V output low. V input low, which is the 17 over 8, minus V output low, which is 0. That's why it's 17 over 8. Noise margin high is 5 minus 23 over 8. Why 5? Because it's V output high minus V input high, right? Which is the 5, that's the V output high, and 23 over 8 is V input high. Okay, of course they are equal in the matched case, all right? And now to the gain. We need to calculate the gain. What is the gain? The gain is defined as the slope of this curve. The slope of this curve. So if you want to calculate the slope, then you define 2 points on the curve, you define 2 points on the straight line, and take the y coordinates, subtract them, and divide them by the x coordinates. This point is VDD as the y-axis, and V input low as the x-axis. So, okay, so this is V input low as the x-axis. So V input low and VDD. While this point is V input high and 0. Why? That's V input high, and it is the y coordinate of this point is 0, right? So you take the y minus the y, VDD minus 0, over V input low minus V input high. Why? Because it's V input low is the x coordinate over V input minus V input high of, which is the x coordinate of the second point. Okay? Subtract them. Of course you expect it to be a negative number because the slope is negative. You could have calculated the gain from another formula, which is Vm minus 0 over Vm minus V input high. So what I've replaced is that I have replaced these two values, VDD and V input low, which is this point. I've replaced it with that point. Okay? Because this point we know that this is Vm and Vm. Alright? Vm, Vm. Right? This is the coordinate of the middle point. So you could take any 2 points and take. So even if I'm not if I'm given the gain, all right, and I do not know what the value of VDD is, and I'm given these two values, all right, I could calculate the VDD or I could calculate the VM, all right. So if I'm given what the value V input high is, and I'm given the gain, all right, I could calculate the value of VM, even if I'm not given the VDD, all right. So this is how you calculate the VDD. This is how you calculate the VM without knowing the VDD. Another example is not a CMOS example. It is an example that gives me where I'm given all of the values of the input low and input high, output low and output high, and what I'm asked for is the noise margin low and high, and the value for the VDD. Why is the value for the VDD required? Because output low, output high, input low and input high are all given in terms of VDD. All right. So let's calculate the noise margin low. Noise margin low is V input low minus V output low. Okay, noise margin low. V input low minus V output low. So 0.4 minus 0.1 VDD. So it's equal to 0.3 VDD. Okay, so it's required to be found in terms of VDD, right? Noise margin high equals output high minus input high, output high minus input high, alright? So it is, so output high minus, yeah, so it's input high, input low, output high, right? So output high minus input high, so 0.8 minus 0.6. Right? Output high minus input high, VDD, which is equal to 0.2 VDD, right? 0.8 minus 0.6, right? So, what is required, in that case, the noise margins are not equal, right? So for this transistor, the noise margins are not equal. And in that case, what we want to do, we want to find the noise margin that is minimum of them, the smaller one of them, we want it to be equal to 0.4 volts, all right? And that's the smaller, so 0.2 VDD equals to 0.4 volts, so VDD equals to 2 volts, okay? VDD equals to 2 volts, that makes noise margin is, the minimum noise margin is 0.4 volts, right? So this is basically what could be calculated for the noise margin. Why is it very effective? It's because the noise margin tells us how good this transistor is if it was affected by noise, right? Let's move on to the propagation delay. Okay, so to the propagation delay. What is the definition of propagation delay? The propagation delay is defined as the time needed for the output to show up at the output of the gate, the output voltage to show up at the output of the gate as a result of applying this input voltage. So if you have a value of an input that is a clock cycle, okay, it goes from low to high, then from high to low, and so on and so forth, and you apply it to an OR gate, then you expect that the output is going to grow like that, and then go like this. All right. So this is the output, and this is the input. All right. So if you try to increase the frequency, which means that if you try to let these two sides of the clock cycle to come closer to each other, then you expect that this will not reach the VDD as expected. All right? Why? Because let's say that you have let the cycle go like this, so it means that this is going to go like that. All right? Which is something that you do not really want to do. So why does it take much time to? It's not an abrupt change. It does take some time because there exists some capacitances that are derived by this NOT gate. And the NOT gate, since the capacitance has to charge and discharge, so that's why it goes up slowly and goes and discharges slowly. All right? So let's first calculate the time of propagation from low to high. So the time taken to go from low to high. It is defined as its value is equivalent to 0.69, that's a constant, multiplied by Rp, and I'm going to define what that is, multiplied by the value of the capacitance C. 0.69 is equal to negative ln half, because you basically do not really want the value to reach VDD. It is sufficient to reach half of the value of VDD. That is how people define the value of time propagation from low to high. All right, so that comes by definition. What is the value of C? C is given, it's something that you measure in the lab, and Rp is defined as the value of the resistance that is seen by the capacitor, which is the value of the internal resistance of this MOSFET transistor. All right. Why is it this value? Because when you are going from low to high, then you have to end up at a high value, which means that this capacitor, that the output is going to be connected to the VDD. All right. So this capacitor, this MOSFET is going to be on, while this MOSFET is going to be off. All right. So that's why I calculate the tau propagation from low to high using the Rp, not the Rn. And similarly, from high to low, I need to calculate using the Rn, not the Rp. What is the value of Rp and Rn? It turns out that using the method of equivalent resistance, there are a lot of methods to find these resistances. Okay, and the one that we are going to talk about is the method of equivalent resistance. Using measurements, empirical measurements in the lab, it turns out that this value of Rp is equal to 30 over W over L, kilo ohms. Right? And Rn is equal to 12.5 W over L kilo ohms. This is N and this is P. So it depends on the value of W and L. It depends on the dimension of this transistor, and this depends on the dimension of this transistor as well. Right? So let's take an example. We know that we've measured the value of the capacitance C to be 10 picofarads. Right? Pico is 10 power negative 12. Right? And the W over L is designed to be 1.25, and W over LP is designed to be 3. What is the value of tau propagation delay from low to high, and that from high to low? Just substitution. Okay, you end up with 30 over W over LP. W over LP is equal to 3, multiplied by the capacitance, which is equal to 10 power negative 12. Alright, so this is 10 power, this is a kilo, so 10 power 3, multiplied by 10 power negative 12, okay, picofarad, alright, multiplied by the 10, okay, because it's 10 picofarad, okay, you get 0.69 times 10 power negative 8 seconds. Right? And similarly, 0.69, 12.5 over, there's a 30 here, so that's 10 power negative 7. Okay, so that is 10 power negative 7 seconds. Right, and there is 12.5 over 1.25, and so on and so forth. Then you end up with 0.67, 0.69 times 10 power negative 7 as well. Right, seconds. Okay. Usually, just because I chose these numbers in such a way that these are going to be equal, that is just by coincidence. But usually you might have the propagation from high to low is larger than that from low to high, or the other way around. From low to high is larger. Why? Because this value of the resistance tends to be higher, and you do not want the dimension of the transistor to be very high, and that's why. So yeah, you could, the change in the dimension of the transistor is the reason why we were able to decrease the value of tau p from low to high. Okay, what is the value of the total propagation time, Tp? It is the average. Tp is defined as the average between low to high and high to low, right? Which is, take the average of these two values, it's approximately it is equal to 0.69 times 10 power negative 7 seconds, right? And if you want to calculate the maximum frequency, so we said that this frequency should not be larger than, so this time period should not be larger than a certain value, which is 1 over f maximum, right? So the maximum frequency is the 1 over the f minimum, 1 over t minimum, right? What is t minimum? It is the sum of these two values, right? Which is twice Tp. Why is it the sum of these two values? Because I need to go up and go down, right? Go up and go down. So you need to add these two values together. So it is equal to 1 over 2, 0.69 times 10 power 7 cycle per second. Hertz, right? And that is the value of the maximum frequency. That is the maximum frequency in theory, right? Usually we work pretty like smaller, like perhaps 10. This is 10 times the typical value that we work at actually. All right, we work on only the 10 power 6 or so. Anyway, so let's continue with this example. So what if we do not have an OR gate? We have another gate. We do not care what it looks like, but it is not as simple as this gate was. All right, it has a number of MOSFETs, not two only. All right, in that case, you do not expect, for the time propagation from low to high, you expect to see Rp only, one value only. Why? Because this value, either this transistor is going to be on, or this transistor is going to be on. If they both are on, then you might expect to see two resistors here, Rp, all right? But and thus the equivalent resistance is half of this value, right? But we do not want to do, we want to take the worst case scenario. The worst case scenario is when just one of them only is on. And that's why the worst case scenario is the same as the NOT gate, right? But for the time from high to low, you expect to see an increase in the resistance. It is not just Rn, you need to multiply by twice Rn because we have two transistors. Why? Because this transistor and this transistor might be on at the same time. And in that case, we have to replace this with equivalent resistance and this with equivalent resistance, and thus the propagation is equal to, from high to low, is equal to 0.69 times Rn multiplied by 2 multiplied by capacitance, where this 2 comes from those two transistors. Assuming that these two transistors are going to be manufactured pretty much similar to that transistor, then you expect that propagation from high to low is going to be twice as much as that of the NOT gate. And that is why we tend to have Rn to be lower than that. We tend to build an Rn, a transistor that is twice as much, has twice as much width as the transistor of a NOT gate, so that whenever we have these two on, we do not end up with a propagation delay that is twice as much, right? And that is why sometimes we say, yeah, okay, this is twice W over L N, and this is twice W over L N. Why this two? So that we can, and W over L N means that refers to the ratio of the width over length of a regular NOT gate, of a regular MOSFET of a NOT gate, right? So we tend to double this by 2, and in that case, you do not expect to see this half, all right? You do not expect to see this half. Well, in that case, yeah, right? You do not expect to see this half, right? So, what is the formula that you're going to use? You could say, yeah, okay, I'm going to use the same Rn, okay? I'm going to multiply by 2, all right? So do not omit the 2. But when you replace Rn, you replace it by 12.5 W over L, okay? W over L of this transistor, which is equal to W over L multiplied by 2. Alright? Which is equal to W over L multiplied by 2. Why is that? Because W over L multiplied by 2 is equal to, so that basically the Rn is defined as 30 over W, 12.5 over W over L of the transistor that you're working on. In that case, our transistor has a dimension that is as twice as big as the regular transistor, and that's why you divide by twice the value of W over L, right? So, what if it was the other way around? The series were in the pull-up network, and the parallel was in the pull-down network. Well, it doesn't really matter that much. In that case, the tau propagation from low to high is the one that is going to increase 0.69 Rn multiplied by 2 and then C, okay? And then multiply by C, right? So, what is the value of Rn? Oh, that's Rp. Okay, what is the value of Rp? 30 over W over L, whatever the W over L is. If the W over L was designed to be twice as much, then in that case you substitute this by 2 W over L, pretty much as we did here, right? So, if the W over L was not equal to 2 multiplied by W over LP, which is that of the MOSFET transistor of the NOT gate, then in that case you do not divide by this value. Right? So memorize this formula, and whatever the W over L that is given in the test, in that case use that particular value. If it's properly chosen, then in that case substitute by the properly chosen value. If it is not, then substitute by whatever value it is given. So the bottom line, substitute by whatever value it is given. Usually, people do not use this notation. Instead, they call it P, which refers to this value. So this is W over L equals to P. All right. So instead, I'm going to give you an exam. I tell you this is twice P, or I tell you that this is 1P. Alright, and this is 1P. If it's 1P, then you substitute by 1P. Alright? You substitute by 1P only. Okay? If it's given as 2P, then you substitute by 2P. And do not forget the number of transistors in series. What if you have a bunch of other transistors and here this is C. Well, in that case, of course, I expect to see the same transistor down below, but in that case, you need to take the worst case scenario. What's the worst case scenario? The worst case scenario is either this on and this on, or this on and this on, right? If you consider that all of them are on, that is not the worst case scenario, because two resistances will be in parallel, and in that case, it is not the worst case scenario. The worst case scenario is when this is on and this is on. This maximizes the resistance, and that is the worst case scenario. All right? So, as the bottom line, let me write down low to high is equal to 0.69 multiplied by Rn, okay, multiplied by the number of transistors in series. Number transistors, number of NMOS, this is Rp, number of PMOS in series. Okay, and then multiplied by C. Okay, tau P, tau propagation high to low, is equal to 0.69 Rn multiplied by number of transistors NMOS in series. Okay, and then you multiply by the C. Rn is equal to, and Rp is equal to, Rn is equal to 12.5 over W over L. Whatever the W over L that is given, which is the number in front of this transistor, in front of this transistor. Okay, if it's twice N, then write down twice N. If it is just one N, then in that case write down 1N. Right? W over L. Whatever that is. Okay? Right now, let's move on to the power dissipation. Okay, so what is the definition of a power dissipation? Power dissipation means the actual amount of power that has been dissipated as a heat in the form of heat energy to the medium, right? Through the resistance Rp and Rn, through the internal resistance of the MOSFET. It is defined as the energy is when you calculate the energy through basic math. You find that that's basic physics. It is equal to the value of C multiplied by V squared. It is equal to the value of the C multiplied by the voltage squared of the VDD. All right? Okay. So, what does it really mean to have this value? Well, when we have an on phase, when the MOSFET is going from low to high, then you expect a charging to the capacitor. From low to high, you expect that the VDD is going to charge the capacitor. And actually what happens is that an amount of energy is dissipated from VDD. And the amount of energy is divided into two portions. And they are equal exactly, those two portions are equal. The first portion is stored in the capacitor, and the second portion is found in the resistance, is dissipated in the resistance Rp. Alright? So, E stored means that it is an energy that is stored here in the capacitor in the form of electrons, in the form of charges. Right? And there exists another portion which is E dissipated, okay, dissipated in the transistor, internal resistance of the transistor, which happens to be equal exactly to this value. And all of this is from low to high, okay, equal to this value. Right? So this is dissipated in the form of heat energy. So if the capacitor, if you give a value of 1, logic 1 here, give a value of logic 0 here, right? So expect to see a logic 1 here. And when this settles down, you end up having a value amount of energy stored equals to C half of C multiplied by V dd squared, right? So what if you turn this from 0 to 1? Well, definitely you expect to see a logic 1, a logic 0 at the output. Okay, logic 1 turns out to be logic 0 at the output. And thus this becomes on, and this becomes off. So the amount of energy that is stored, which is equal to half CV squared, is going to be dissipated in the Rn. So by the end of the day, you expect that the entire energy, which is CVDD squared, is going to be dissipated in the form of heat energy. Half of it is going to be dissipated in the Rp, and the other half is going to be dissipated in Rn. How is it going to be dissipated in Rn? Through the discharging of the charges from the capacitor in the high to low phase. Alright? So you expect to see charging and discharging. Okay? Charging and discharging. Alright, so this is the energy stored. If you want to calculate the power dissipated, well, you definitely need to divide this energy by the time, which is the period. What is the period? It is 1 over the frequency, so you multiply it by the frequency f. Multiply the energy by the frequency f, and thus CVDD squared multiplied by the frequency f. Alright? So let's take an example. If you are given a voltage VDD equals to 1 volt, and the frequency is 2 gigahertz, right? And the capacitor is 10 picofarads. Find the energy dissipated from the VDD, which is the same as the question of find the energy of charging and discharging. Well, the energy of charging is half, and the energy of discharging is also half, right? Which means that that's the total energy that is charged and discharged, right? So energy dissipated equals the energy charged plus energy discharged, right? And that's why E dissipated equals CV squared. Dissipated. The total amount of energy is going to be equal to C multiplied by V squared. 2 times 10 power 9 multiplied by 1 squared. Okay? And that is equal to 2 times 10, 2 gigajoules. Right? 2 gigajoules. What about the value of the energy, the I average? If you want to calculate the I average, you need first to calculate the power average. Why? Because you know that the power average is equal to I divided by the volt. Power average is equal to I multiplied by the volt. So the I average equal to P average over VDD. Right? What is P average? P average equals, oops, I made a mistake. That is, I multiplied the frequency, not the capacitance. So this is 10 picofarad multiplied by 1 squared, which is equal to 10 picojoules. 10 picojoules, right? And this is 10 picojoules, which is the energy, multiplied by the frequency, which is 2 gigas over VDD, which is 1. So that's equal to 20 watts, 20 amperes. Right? This is equal to 20 amperes. So if you want to decrease the value of the voltage by half, okay, so VDD equals half, you want to decrease the power dissipated, so you expect that the P average is going to be equal to 5 watts, right? Why? Because half here is squared. P average equal to C multiplied by V squared. So decreasing it by a factor of 2 decreases the power by a factor of 4. On the other hand, decreasing the frequency by a factor of 2 decreases the power by a factor of 2 as well. So it's more efficient to decrease the value of the VDD because it decreases the power non-linearly. Alright? So I hope you guys had a good grasp of these 3 topics. And if you have any questions, please let me know.